All right, so looking at today, we're going to look at the very last lesson of our Unit 7, looking at our similarity unit. Today, just looking at some proportions and triangles. And you can see up here we have three theorems we're going to talk about today. The side splitter theorem, triangle midsegment theorem, and triangle angle bisector theorem. So starting over here with the side splitter theorem. So the side splitter theorem just occurs when you have a side that is parallel to one of the sides of the triangle. So in this case, you can see that they've told you that MN is parallel to AC. So just remember these double vertical bars here mean that the lines are parallel, or also you can see that they have the arrows marked through. So either of those let you know that those two lines are parallel to each other. So this theorem only applies when you have these parallel lines. Theorem states that if you have these parallel lines, right, so a line that is going through the triangle, splitting the two sides, that you have this proportion created looking at the two sides that got split. So as you can see in this fraction down below, we have AM over MB. As you look, AM and MB are both a part of the same side. So here in one side that got split, you're going to create a fraction. And then you're going to take the second side that got split. In this case, this side BC got split by that parallel line, and you're going to use that to create your second fraction. So within the fractions, right, depending on how you write the first one, you just want to make sure that it matches up with what's across from it. So here AM, as you can see, is across from NC. So both of those would go up top, and then MB would be across from BN. So both those would be corresponding or go together on the bottom. So each individual fraction, just to reiterate, is coming from one side of the figure. So AM over MB came from the left side of the triangle. CN over NB comes from the right side of the triangle. And then you just want to make sure that your corresponding parts are both on top, corresponding parts both on bottom. So looking at the second theorem here, we're talking about the triangle midsegment theorem. So this occurs just similar to our trapezoid midsegment theorem when you have a segment that is at the midpoints of your two sides. So there, if you look at points G and H, point G would be the midpoint of side DE. So you can see there with the marks that they put through those that GD and GE are congruent, which they've marked up above. And then H would have to be the midpoint of EF. Since it's splitting EF in half, EH and HF would be congruent. So the midsegment, remember, is just a segment that is connecting the midpoints of two sides of the figure. So we took a look at the midsegment of a trapezoid. Same thing occurs here with the midsegment of a triangle. So if you recall here, the midsegment of a trapezoid, remember we were trying to find the midsegment by taking one half of the two bases added together. So in this case, to find GH, or the distance of that midsegment, now that there's not two bases in this triangle, like there was in a trapezoid, all we're doing is taking one half of that side DF. So one half of DF. So just quickly for an example, right? If they told you here that DF was a distance of 22, to find GH, all you're going to do is end up taking one half of 22. We're taking one half, multiplying it times 22. So in that case, you can see that GH would come out to be 11. So the midsegment, as long as it is connecting the midpoints, that midsegment is going to be one half the distance of the base of that triangle. The last theorem we'll take a look at today is this triangle angle bisector theorem. So looking at the triangle angle bisector theorem, it occurs when you have an angle that is getting split in half. So there you can see through the marks on the diagram and through that statement that this angle, the total angle at V, is getting split in half. So we have two congruent angles that are formed. Angle UVX would be congruent to angle WVX. So this ray right here that is splitting that angle in half would be called the angle bisector. So in this case, our angle bisector would be this ray VX. So looking at the proportions you're able to create when you have an angle bisector down here, just recognize that for this one, you want to make sure that you're taking the values on one side of the angle bisector. So in this case, if I just look at the left side first, both those sides are UX and UV. So notice that here, both of those would go on the top of the fractions. So right away, you just want to take two of the sides, or two of the segments that are on one side of the angle bisector, put both of those up top. So now down below, you're going to match them up with the other side of the angle bisector. So in this case, we have the sides WX and WV. So just to make sure that you get these things in the correct location so that your proportion actually works, let's look at this first fraction. So within the first fraction, we have UX and WX, UX over WX. Notice that both of those are parts, right? So they're parts of that bottom third line, or bottom third side of the triangle. So you can see that UX and WX are not total lines of the triangle. That is the side that is getting split by the angle bisector. The other fraction, UV and WV, would be whole sides, right? So these are both whole sides of the triangle. So making sure that you're just matching it up so that your whole sides are creating a fraction, your parts are creating a fraction. Both values up top of your proportion come from one side of the angle bisector. Both values on the bottom side of the fractions come from one side of the angle bisector. So we'll take a look at each of these theorems here as we work through some of these examples. And then I'll do some of them here and then let you try a couple on your own. So starting with number 1. As we read through problem, it says DE. Remember, these double vertical bars just tell you that these lines are parallel to each other. So sometimes helpful just to go ahead and make that mark on the graph just so that you get used to seeing it. Sometimes they might not word it out for you. They might just have the arrows on the graph, and you have to realize that that means that those two segments are parallel to each other. So now that we know that DE and AC are parallel to each other, the next step is we have to find the value of X. So before we do that, in order to set up this proportion, I'm just going to highlight these sides here so you can see that on the left here we have two segments, AD and DB. On the right, we would have these two segments, BE and EC. So going back right to the theorem, very similar to the theorem right above, the side splitter theorem. So anytime we have these parallel lines, what's going to happen is you're going to want to create a fraction based on one side of the triangle. So in this case, I'm going to use the left side and put that one up top. So there we have the two sides BD and DA. And now as I go to create my second fraction for my right side, I just want to make sure I match up the corresponding parts, right? So looking at BD, if I go straight across from that segment BD, I know that BD would correspond with BE on the right side. And then DA across from it would correspond with EC. So right away, I'm just going back, right, to set up those proportions. We just want to make sure that the values in our first fraction come from the same side of the triangle. The values in our second fraction come from the same side of the triangle. And then we're just matching up the corresponding parts. So now what we have to do is plug in the values we know here. So BD is a distance of X. DA was a distance of 6. BE was a distance of 12. Then EC would be a distance of 4. So now to solve, just like we've been doing with our similarity unit, to solve the proportion, you just need to cross multiply now. So multiplying across these diagonals. So we'll start with the diagonal that includes X. So multiplying across this diagonal, 4 times X would get you 4X. Just remember when we do our cross multiplication, we're just setting each diagonal equal to each other. So across our other diagonal, 6 times 12, we'd end up with 72. Last step is just to solve that equation there, 4x equals 72. So simply by dividing by 4 on both sides of the equation, we get x is equal to 18. So here that distance, that missing value of x in our diagram would end up being a distance of 18. So there you can see that if you plug that value back in and cross multiplied, those values would come out to be the same. So those fractions would be equal. Any questions over that first one there? So looking at this next one, example 2, first step they want us to do is just to solve for x. All right, so just to solve for x, in order to do that, we're going to use our side splitter theorem, recognizing here that we have a couple of parallel lines. So you can see here that you have these parallel lines going across at ST and PR. So those are the parallel lines we're going to use just like we did in this problem above to set up some proportions. So as I look here on the left side, remember we just want these segments that are getting created by these parallel lines. So this first one on the left, we're going to call PS. Remember, underneath it, we want to create the same segment. So in this case, looking at it, now since we're just using our parallel lines now, we're going to ignore that segment UV for a second. So the other portion that we want to use would be this total distance of SQ. So on the other side of our triangle, breaking down the segments again. So the first one, in between these parallel lines down below, we're going to use this segment here, TR. So I'll put that one directly across from PS. As you can see that TR and PS, both those are the bottom segments of their individual sides. And then up above, we're going from the parallel line all the way to the top of the triangle and using QT. So there you can see that SQ and QT, those segments are across from each other. So there we have our proportion where we can go fill in the values and use that to solve for X. So to set it up, PS was a distance of X plus 2. So anytime you have an expression, I would just encourage you to go ahead and throw some parentheses around that so you recognize that those things are connected. On the bottom, SQ. So if we want the total distance from S to Q, we want to make sure we're adding those two pieces. So the 4 and the 12 combine to make 16. On the other side, TR ends up being a distance of X. And then QT would be, here once again, adding up the two little pieces we know, QT ends up being a distance of 12. So now we have this proportion that allows us to cross multiply and then solve for X. So let's look at what it would look like once you cross multiply here. So multiplying across the first diagonal, 16 times X would just be 16X. Across the other diagonal though, just make sure here, sometimes it's helpful to put the parentheses on it too, just so you recognize that you should be distributing, right? So really across this other diagonal, when we take the 12 times the X plus 2, you can imagine it here that the 12 would be out front times the expression X plus 2. So that kind of is a nice reminder that you need to go distribute the 12 and multiply it times each of those values in parentheses. So 12 times X is just going to give you 12X. 12 times 2 ends up being 24. So final step is just to go solve. So as we solve here, just subtracting the X terms, subtracting 12X from both sides to get the X terms to the same side. It's going to cancel it out for you over there on the right. On the left, you're going to be left with 4X. One thing on the right now is 24, and then just dividing both sides by 4 is going to get us our solution for X. In this case, X would be equal to 6. So the question there was just asking us to solve for X. So in this case, we know TR would be 6. And then over here, if we took 6 plus 2, we know that this distance PS would then end up being a total distance of 8. Next question down below, asking us to solve for Y now. So looking at it, now that we know these distances, there's a couple ways that you could do it. You could use those similarity, side, angle, side similarity that we talked about, or side, side, side similarity. Or what we can do here is to use our mid-segment theorem. So now that we've already solved for X, and we know the distance there of PS and TR, now you can look back and see that we're going to have a mid-segment or a midpoints here. I'm just going to erase this so you can see it a little better. So looking at it, we said that this PS was now a distance of 8, right? Once we plugged in the 6 for X. Over here, TR was a distance of just 6. So now as you look at it, what is the midpoint or the point halfway in between P and Q over there on the left? So as you look at it, here you can see that the distance from P to U, if we add both those values together, 8 and 4 would be 12, just like U to Q would be 12. So here really, U ends up being the midpoint. So we have from P to U, that total distance is 12. Just like from U to Q, that total distance is 12. So U is directly in the middle of those points, P and Q. Same thing over here with V. Looking at V, we know that QV was a total distance of 9. And then if we add these two segments down below, 3 and 6, we know that gives us a total distance of 9 as well. So V has to be the midpoint looking at that side QR. So here if we have the midpoints, we're going to use our mid-segment theorem. So just going back up top here just to quickly show you it. The mid-segment theorem, right, is just saying that in order to find this missing distance, in this case they were looking for GH, so G and H were the two midpoints in this triangle. All you have to do is take 1/2 the distance of the base of the triangle. So the base side that is going across just like the mid-segment. So down here with this example, which one is our mid-segment, which one is the base? So looking at it, our mid-segment really is just this side, UV, that we're trying to find. The distance of Y. So the base that would be running the exact same as that would be this very bottom of the triangle, PR. So if you set it up using that mid-segment theorem, here in order to solve for the distance between U and V, all we have to do is take 1/2 of the distance of PR. So plugging in what we know, UV we said was a distance of Y, PR was a distance of 30. So all we have to do is take 1/2 times 30, which gives us 15. So there Y would end up being 15. And that will get you that distance there of UV. So that is just an example of how you would use the mid-segment theorem with a triangle. So very similar to what we dealt with trapezoids. Last part here, solving for Z. So this one, it's a little bit trickier, but it's going back to using some of our similarity properties here. So all we have to do is be able to set up a proportion, recognizing here that we have some side angle side similarity going on, making sure that these triangles are indeed proportional to each other. All right, so I'm gonna erase some of this just so you can see a little better as we start to look at this next part of the problem. Looking at this problem to solve for Z. So now that we've solved for X and Y, we have some of these distances available to us in this triangle diagram. So the first triangle we're going to take a look at is this smallest of the three triangles, this triangle QUV. So I'm just going to quickly write out a similarity statement so that we can match up here our corresponding parts to solve for this missing segment. So looking at triangle QVUV, all I'm going to try to do is try to match that up with the corresponding parts of our middle triangle here. So if you think about the triangle now that goes from Q to S to T, we're trying to use that triangle as well. I'm recognizing that these two triangles are going to have to be similar triangles because they have congruent angles, right? They both have angle Q, which is congruent. And then since we have some parallel lines here, we know that the other two angles are going to be congruent as well. So as I look to match it up, I know that angle Q is going to match up with angle Q. In this case, angle U would match up with angle S. Angle V would match up with angle T. So there's our similarity statement. Triangle QUV is similar to triangle QST. So now I'm just going to create a proportion that allows me to then solve for that variable Z. So I'm going to start just with that triangle in blue. So if I'm trying to find Z, really, that is the side ST. So I'm going to make sure I create that side of my proportion. And then I just need to choose another side of that triangle highlighted in blue. So it doesn't matter what side we want to use here. I'll just go ahead and use the side QT. So both of those values, right, coming from that triangle in blue. Next, we want to just go match it up with the corresponding parts for our triangle in yellow. So you can do this also just by looking at the similarity statement. So looking at it, ST would match up with the side UV. And then QT would match up with the side QV. So you can look at the diagram to match those up, or you can once again just look back here at the similarity statement you just created to match up those corresponding letters. So now we can just replace with the values we have for each of these distances. So ST was a distance of Z, UV was a distance of 15, right? Since we just solved for Y, we knew that UV now is 15. So looking at the other side here, what is the distance of QT as you look at the diagram? So looking at the distance of QT, QT ends up being a total distance of, here you want to add the 9 and 3 together to get 12. And then on the bottom, QV would be a distance of 9. So this just gives us a quick proportion that we're able to use to go solve for that last variable Z. So now you're going to try to multiply across these diagonals. So 9 times Z just gets you 9Z. Then you want to multiply across the other diagonal. So 12 times 15 ends up being 180. So then we just need to divide by 9 on both sides to get that distance of Z. So in this case, Z would be equal to 20. So that's just going back to using your similarity theorems to set a proportion to solve for that last variable. So we're going to flip it over here, take a quick look at the corollary to the side splitter theorem. So this is very similar. You're going to pretty much do it just like you would those side splitter problems. Here you just have multiple parallel lines that are intersecting with two different transversals. So if you can imagine this, right, if you extended these transversal lines, eventually these lines are going to meet and form a triangle, right? So it's just like the side splitter theorem here, sides of the triangle are just getting split by these parallel lines. So just like we talked about earlier in the side splitter theorem, one fraction is going to come from one side that was split. So here in this case, the parallel lines are breaking up these two segments here, AB and BC, and then the ones across from it would be DE and EF, right? So just notice here that depending on how you set up the first fraction, you want the second fraction to be matched up with the parts that are directly across from it. So there, AB would be directly across from DE, just like BC is directly across from EF. So then you would just cross multiply just like before to go ahead and solve. So we'll take a look here at example 3. It says a reflecting pool is separated by walkways parallel to Lincoln Street and Jefferson Street, which are parallel to each other. So how much tiling does X feet represent? So here the parallel lines they're saying are these walkways that are parallel to the streets. So we have all those parallel lines happening there. They're asking us just to figure out what X represents. So now to create my proportions, all I need to do is take the values from one side here. So I'm going to take the top side first, the one that involves X. So there, we're just going to use 2 of these segments that were created by the parallel lines. So in this case, I'm going to use X and 60 to create a fraction using that top side. And then going down here along the bottom side, along this Spruce Street, we want to use the distances of 24 and 72. So just making sure that we're matching it up. 24 is directly across from X, so that needs to go up top. 72 is directly across from 60, so that needs to go down below. So the last step here, now that you know your proportion, is just to cross multiply. So 72 times X just becomes 72X. And then across our other diagonal, we're taking 60 times 24. Just want you to plug that into your calculator. 60 times 24 is going to get you 1,440. And the final step, right, we're just dividing by whatever the coefficient is in front of X. So in this case, we're dividing by 72. And as you divide by 72, you see that X comes out to be a distance of 20 feet. So I'm going to let you pause the video for a second and take a look here at this next example, trying to find the distance of Y. So now you're going to do the same thing here. Just now you want to make sure that you're using the right 2 segments probably. or now that you know x, you can use that segment as well. But you probably just want to be using these segments here, middle segments and the right segments to create a proportion. So I'll give you a second here to take a look and try that. All right, so looking at setting up your proportion, if your proportion doesn't look exactly like that, there's a couple options, right? So yours doesn't have to look exactly like your neighbor's. So biggest thing here is that within your fraction here, the 60 and the 24 should create one fraction. So you could have had it as 60 over 24 or 24 over 60. And then depending on how you set up the first fraction, the next fraction, you would want to make sure you put the sides that are directly across from it. So either 72 over y or y over 72. Once again, if your fractions, as long as those fractions individually look the same, it doesn't matter what fractions on the left, what fractions on the right. So you might have had the 60 over 24 on the right side of the equal sign, the 72 over y on the left, and vice versa. But either way, right, once you go to cross multiply, you'll see that regardless, the 60 diagonal will be multiplied with the y, the 24 diagonal multiplied with the 72, and then we end up getting y is equal to 28.8. So the last theorem we'll talk about here, the third theorem, the triangle bisector theorem. So as you look at the triangle bisector theorem, here you're taking whatever is bisecting the angle. In this case, we can see that BD is splitting that angle at B. So what we have to do is create our proportion. We're taking the values that are on one side of the angle bisector, making sure that we're putting those up top. So in this case, I'm just going to use AD and AB, place those values up top since both of those came from the top side of that angle bisector. And then now down below, I want to use these values of CD and CB since those came from below the angle bisector. So the only thing you want to do is make sure that you're matching it up with the correct fraction. So AD was just a portion of that third side of our triangle, so that gets matched up with CD since that is the other portion of that side. AB was an entire side of the triangle, just like CB would be the entire side of a triangle. So once you have that, sometimes it's helpful just to do it in letters first. We're just going to replace it with information we know. So AD, we know is a distance of X. AB was a distance of 10. CD, so this is one we're going to have to go find out real quick. So as you look at CD, if we know the total distance from A to C is 13, and the distance from D to A would be X. To get this distance from C to D, really, we're going to use the expression just 13 minus X, because whatever X is, once we take it away from 13, gets us that remaining distance of CD. So underneath the fraction that has X, we're putting 13 minus X. Once again, I encourage you to put those in parentheses, just so you remember to distribute. And then lastly, the distance of CB would be 16. So once we get our proportion set up, we can cross multiply. So 16 times X is just 16X. In the other diagonal, we're taking 10 and multiplying that times the expression 13 minus X. So remembering to distribute the 10 there. That side looks like 130 minus 10X. On the other side, we have 16X. And now we're just using opposite operations to try to solve. So in this case, adding the 10X, we'll get that to cancel out over there on the right-hand side. So 16 plus 10X gets us 26X equals 130. Then your final step there would be to divide by 26. So in this case, what do we get X to equal? So 130 divided by 26 gets us a distance of 5. So a lot of people stop here as soon as they solve for the variable. Just make sure, and we talked about it a ton of times, but make sure you look to see what the question's asking. In this case, they're asking you to find AD and DC. So for your value of X, all you gotta do is plug it back in there. So in this case, AD would end up being just X, right? Or 5. And then to find CD, all we're gonna do is plug in the value of X. So really we're taking that 13 minus 5, which gets us a distance of 8. And there you can see that both those distances together add up to that total distance, 13. So make sure if you're asked to find the actual distances, you plug back in your solution for your variable. So the last one, is set up exactly the same, so you can try that one on your own in your group here. So take a second to give that one a try, and then pause the video. And then when you've given it a try, you can see if your answer matches mine. So here, you just want to check your answer right. Once you cross multiply and use some opposite operations to solve, we get x is equal to 9. And then just remembering that they're asking for the distance of gh and gk. All we got to do is plug 9 back in for x and evaluate those expressions. So 3 times 9 plus 3 gives us 30 for the distance of gh. And then 3 times 9 minus 7 gives us a distance of 20 for gk. So now you can use the remainder of the class time to work on this assignment or previous assignments here from this Unit 7 lesson. Just make sure that you recognize that this is the last section of Unit 7. So that means next class on Monday, we will review the entire unit, and then your test will be on Wednesday.